Okay, so let's continue for our chapter of the capacitors. Okay, so in this lesson, we're going to talk about the charging and discharging of the capacitor. Charging and discharging of the capacitor. So in this lesson, there is two subtopics we are going to concern about. So let's talk one by one. So we'll begin with the charging capacitor. Okay. So in this case, we have the charging CR circuits. So as a note, this C is actually denoted as the capacitor, and this R is actually referred to resistor. Okay, this one is the resistor, and this one is the capacitor. Okay, so in this topic, we are going to talk about the derivation of the charging CR circuits. Derivation of charging CR circuits. So let me just drag it down. Okay, so derivation of the equation contains the electrical charges, the potential difference across the two plates, and finally the electric currents. So we have at least three equations that we need to derive. Okay, so first of all, we have we need to draw out the circuit so that I can explain more easily. Okay, so this one should be the capacitor. Okay, and I have the resistor. So that is why the circuit is called the CR circuit, which contains the capacitor and the resistor. Okay, so if we are going to charge the capacitor, of course, we need to have the power source. And this one is the battery. Okay, so let's join all of them together. So this one is actually joined to this one, and this one is okay. And this one is actually attached to the battery. Okay, let me see what else. Okay, I think that's all. So there's actually three components in the charging CR circuits. Okay, alright, so this is the capacitor, and this one is the resistor, and this one is the power source. Okay, so initially, okay, let's say I have a switch here. So let me just use another color, and this is my switch. And this is the switch. So when the switch is closed, the charging when the switch is closed, the charging process is about to begin. Okay, so when the charging process begins, the time t initially is actually equals to 0. So our time taken to charge the circuit to charge the capacitor for the initial time is actually 0. Okay, so we have the initial potential difference in this circuit. So this is actually V naught means the total potential difference which exists inside the capacitor and the potential difference across the resistor. Okay, so since this one is the capacitor, so the potential difference we denote it as Vc, and this one is the resistor, and the potential difference across the resistor we denote as Vr. Okay, so since this circuit is actually the series circuits, so based on the previous knowledge, we know that the total potential difference is across the series circuits is actually equals to the sum of the potential difference of all electronic components which involve inside these circuits. So what I have here is actually V naught. V naught is actually the sum of the potential difference across the capacitor and the resistor. Okay, so this is the Vc plus Vr. Okay, so what I have here is actually, so what if I express this as Vr? So what I have for my Vr is actually equals to V naught minus Vc. Okay, so alright, so since the potential difference across the resistor is actually equals to IR, so initially the potential difference which, so let's say my direction of my current is actually this way, since this one is the positive and this one is the negative. So since the direction of the current is here, so it means that the current will flow through the capacitor first, and the next will be the resistor. Okay, so this V naught, which is the potential difference, is actually means the initial potential difference across the capacitor, or I can say that this is actually this V naught. So this V naught is actually means the maximum potential difference across the capacitor. So this is actually the maximum value, so not the, so it is not the concept that the current will flow through the capacitor first and the second will be the resistor. Sorry, so that concept is actually wrong. So this V naught is actually means that V naught is actually means that the maximum potential difference that can be obtained from the power source for the capacitor. Okay, so since this is this refer to the potential difference across the capacitor, so we know that my Q is actually equals to CV. So since this one is the naught, which is the maximum potential difference across the capacitor, so since this one is the maximum, and hence the electrical charges which obtained from the maximum potential difference is actually also maximum. So this one C is actually, okay, sorry. So if I derive the expression for the V naught, what I have here is actually equals to Q naught over C. So this one is actually Q naught over C. Okay, so this is actually at time t, sorry, not time t. So this one is actually when t is actually equals to 0. So after a few times, when the time taken reach time t, so the potential difference across the capacitor will become Vc. So this one is the Q over Q over C. So the Q will be decreased to Q, and C will remain constant since this one is the capacitance of the capacitor. Okay, so let me see what else. Okay, so alright, so I think let me just erase all this one. Okay, let me erase this one. So this one as well. Okay. So we continue this equation. So if I move this C to another side, so what I have here is actually CIR equals to Q naught minus Q. Okay, let me just erase this one. So we know that from one equation about there's actually the relation between the Q and the electric current. So which is the equation of Q is equal to IT. So I is actually equals to the rate of change in electrical charges. So which means that I is actually equals to dq over dt. Okay, so CR dq over dt, and this is the Q naught minus Q. Okay, so alright, so let me just see. Okay, so if I move this one to another side, so what I have here is actually dq, and this one is actually 1 over CR dt. So if I about to integrate this both sides, so this one is actually the value is actually from the 0 to Q. Not 0, sorry. Wait, let me just observe for a while. So let me just see for a while. Okay, yeah, the value is actually from the 0 to Q. Since the circuit is charging the capacitor, so the 0 will be rise from 0 to Q. And this one, as for this one, since we start with the time at time which is equal to 0, so this one is the 0 and this one is the t. Okay, so what we need to do is actually just integrate. So to be note that this one is actually a value which is not the Q, not the variable. So this one is considered as the constant, and hence what I get for the integration of these sides is actually equals to the ln Q naught minus Q. So what I have here is actually Q0 is equal to, so this one integration of 1 over CR, which is in terms of T. So what I have here is actually T over CR. So this is T0. So what I have is, if I expand both sides, so this one is the Q and minus ln Q naught minus 0. So it's equal to T over CR. So if I about to combine these two ln, so what I have here is actually equals to the Q naught minus Q. So the substitution is actually equals to the derivation, not derivation, sorry, is equals to the division. Okay, so this is the Q naught. So this is the T over CR. So let me just drag it down. Okay, so if I move this ln to the other side, so what I have is actually the exponential to the power of T over CR. Okay, so this is Q naught minus Q over Q naught. So let me just erase this one. There's no enough space. Okay, let me just erase this one. Okay, so we continue here. So what I have here is actually Q naught minus Q. If I move this Q naught, the base Q naught to the other side, so what I have is actually Q naught multiplied by exponential to the power of T over CR. Okay, so what I get finally is actually Q is equal to the Q naught minus Q naught E T over CR. So if I about to factorize this Q naught, so what I have here is actually 1 minus E T over CR. So this is Q. And if I, so this is the equation for the electrical charges for the CR charging circuits. So if I about to draw a graph, so what I have for the graph, so this is Q and this is T. So this is the asymptotes for the exponential graph. So what I have here is actually this one, this type of curve, which is the 1 minus E. So this curve is actually referred to the exponential graph, and this one is actually the Q naught, which is maximum charges. So from this graph, we know that the electrical charges is actually increasing when the battery is supplied to the CR circuits, or I can say that the capacitor is actually in the condition of charging in the CR charging circuits. So this is the equation for the electrical charges. Okay, so let's just move on to the potential difference. So what will happen to the potential difference across the capacitor? Okay, let us just see step by steps. Okay, so as for the potential difference, so we know that the electrical charges is actually equals to the Q naught, Q equal to Q naught, so brackets 1 over E minus T over CR. Okay, so since the Q is equal to CV, so what I have here is actually CV, and since this one is maximum, so the potential difference across the capacitor is also maximum. Okay, so this is 1 minus E negative T over CR. Okay, so this C can be cancelled from the both sides. So this is the V naught 1 minus E T over CR. So this is the final equation for the potential difference. Okay, so as for the graph, so the graph is basically same as the graph that we draw just now from the electrical charges. So this is the VT graph, and this one is the asymptotes. So the asymptotes, the value for the asymptote is actually the maximum potential difference across the capacitor. So this one is actually curve. Okay, so this is the potential difference across the capacitor. Okay, so we've done for the potential difference and the electrical charges. So what will happen to the electric current? So this one. So this time we are about to derive the electric current. Okay, so this is the electric current. So electric current, we actually explain the electric current in the circuits instead of capacitor. So to be noted that this electric current is actually the current which inside the circuit instead of electric current. Okay, so same as before, we start at this equation. So Q is actually equals to the Q naught 1 minus E to the power of negative T over CR. Okay, so we know that from the previous parts we talked about Q is actually equals to I over T. So we know that I is actually the rate of change in the electrical charges, which is dQ over dt. Okay, so if I about to get this electric current, so what we need to do is actually differentiate this equation. So if I going to differentiate this equation, so dq over dt, what I have is actually this q naught which remain constant. So this q naught is a value. So this 1 over t. So for this exponential, so what I have here is actually, if I about to differentiate this exponential t over cr, so I know that the d dx for the exponential fx is actually equals to f prime x, so the exponential remain constant. So this is the differentiation rule for the exponential. So if I about to derive this, differentiate this one, so what I have here is actually 1 over CR. So this time, for this side, the t is actually the variables that need to be differentiated. So 1 over CR, sorry, this one should be the negative. So this is the negative 1 over CR since the t has been differentiated. So the exponential remain constant, remain exists in the equation. Okay, so sorry, this one should be 0 since there is no variables for this 1 anymore. So 1 after differentiating is actually equals to 0. So this q naught, so negative negative, what we get is actually positive. So 1 over CR E minus CR. Okay, so this dq over dt is actually I. Okay, so since this q over c, so q is equal to cv naught, q naught is actually equals to the cv naught, so the v naught is actually equals to the q naught over c. So what I have here is actually the v naught over r multiplied by the exponential to the power of negative t over cr. So what I have here is actually the maximum electric current. So this one is the final equation. Okay, so what will happen if we draw the graph of electric current against T? So what I have for the graph is actually this is I and this is T. So this is actually the maximum electric current. So what I have is actually this graph. Okay, so initially, when the power supply is about to charge the capacitor, so initially the electric current inside the circuit is actually maximum. When after the capacitor is about to charge, when the capacitor is charging, so the electric current inside the circuit is actually keep decreasing until infinity. So when the capacitor is actually fully charged, so the capacitor is fully charged, so I can say that there is no more electric current inside the circuits, but it is impossible. This is because the exponential graph told us the curve of the exponential curve is will never touch the x-axis unless it reaches infinity. Okay, so I repeat again. So initially, my current is actually maximum when the electrical charges is about to charge up the capacitor. So the electric current inside the circuit will decrease exponentially. So when the capacitor is fully charged, so I can say that there's no more electric current inside the circuits. So but it actually takes a long time, or I can say that it is impossible. This is because the exponential curve will never touch the x-axis or the t-axis, whatever. So I can say that the electric current inside the circuits will never reach zero unless we we allow it to charge up for a long time. So at a certain time, so the electric current will inside the circuits will be totally zero. Okay, so this is the concept for the electric current inside the circuits. Alright, so let us move on to another part. So we are still inside the subtopic for the charging CR circuits. Okay, let me just erase this one. Okay, so let's talk about the time constant. So the time constant, which is this t, the t-like symbol. So this one is considered as the time constant. So the time constant is actually equals to CR. So CR at certain time, when the time is actually equals or approximately equal to the value of multiplication between the capacitance of the capacitor and the resistor. So from the equation, Q is equals to the Q naught bracket 1 minus e to the power of negative t over CR. So when the value of this t is actually equals to the CR, so let's see what will happen here. So if my t is actually equals to CR, so what I can do is actually cancel each other. So what I have here is actually 1 minus e to the power of negative 1. So if we use the calculator to calculate the value for 1 minus e to the power of -1. -1, okay, so what I have here is actually 0.63 q naught. So this is the first time constant. So this is considered as first time constant. So what will happen for the second time constant? So okay, let me erase this one. So this is actually the first time constant. So what about the second time constant? So the second time constant is actually equals to the 2 times of CR. So what I have here, okay, let me just erase this one. Okay, so this one is actually Q naught 1 minus E -2 CR divided by CR. So if I cancel each other, so what I have here is actually 1 minus e to the power of -2. So what I have for the final value is actually 0.865 q naught. So just now it's actually equals to the 0.65 if I'm not mistaken. As for the second value, it's actually equals to 865 q naught. So this indicates that for the first time constant, the value for the electrical charges inside the capacitor, which is stored by the capacitor, is actually 65% from the maximum electrical charges. As for the second time constant, the electrical charges stored by the capacitor is actually equals to the 86.5% of the maximum electrical charges. So based on these two values, I can say that the electrical charges which stored by the capacitor is actually increasing. So this is why the I can say that the circuit is actually charging the capacitor inside the CR charging circuits. Okay, so I think that's it for the charging capacitor inside the CR charging circuits. So let's move on to the discharging circuits. Okay, let me just erase this one. So in this subtopics, we're going to talk about the discharging circuits, discharging of the CR circuits. So in this case, the component that involved is actually consists of the capacitor and the resistor only. So this is actually the resistor. So this is the capacitor. So the resistor has the, okay. So this is the, okay, capacitor, and this one is the circuits. Okay, so there's actually a switch here. Alright, so if we are going to discharge the capacitor, so the battery, the power supply is actually not necessary to attach inside this circuits. So if the battery is not involved in this circuits, so the capacitor is actually start to function. So its function is actually by releasing the electrical charges. So the capacitor release the electrical charges in the form of electric current. Okay, so I can say that my electric current is actually equals to the negative dq over dt. So this negative is actually due to the decrease in the electrical charges inside the capacitor after releasing the electrical charges for a few times. So if the electrical charges inside the capacitor decreases, and hence the electric current inside the circuit will also decrease. So this negative sign is due to the decrease in electrical charges inside the capacitor, causing the electric current, okay, let me just drag down, causing the electric current inside the circuits to be decreased. So this is actually the concept for the negative sign, which shows that the magnitude for the electrical charges inside the capacitor is actually decreasing when the capacitor is start to discharging. Okay, so hence the electrical charges will decrease. So this is the concept. Okay, so let's see what will be the equation for the electrical charges and the potential difference across the capacitor and the electric current, same as the equation that we discussed from the charging circuits. So in this case, we are going to talk about the electrical charges, the potential difference across the capacitor, and the electric current inside the circuits. Okay, so let's begin with the electrical charges. Okay, so we know that for the series circuits, the potential difference across the series circuits is the sum, or I can say that is the total of all of the electric components inside the circuits. So when we observe for this diagram, so I can see that there's only two electrical components involved inside this circuit. So my VC is considered to be the power supply. This is because it is the one that released the electric current. So my VC is actually equals to VR. Okay, so since Q is equals to the CV, so V is actually equals to Q over C. Okay, so this is the Q over C, and this one is the IR, which is the potential difference across the resistor. Okay, so my Q is actually equals to the CIR. So since my I is actually equals to the negative dq over dt, so hence I can substitute this I as this one. So this one is the I dq over dt, and this is the CR. Okay, so what we need to do is actually integrate this differential equation as the basic solution. Okay, basic equation, not solution. Okay, so So let's see how can I move this equation properly. So what I get is actually 1 over CR, and this is moved to the other side, and this dt is moved to the other side, and CR is actually moved to the other side as well. So this one is dt is equal to, okay, let me just observe for a while. Okay, so this dq and this one should be 1 over q. Okay, so the value, of course, this one is the from 0 to t, and this one is actually equals to the, let me just observe for a while. So this one is actually q naught, and this one is q. Is it correct? So let me just observe for a while. Okay, so yeah, this is the integration of the electrical charges. Okay, let me just erase this one. So the value for the electrical charges is actually varies from the maximum charges initially until the magnitude of the certain magnitude of the electrical charges at certain time. So if I about to integrate these two sides of the equation, so 1 over q basically is ln q. So this is the q, and initially the electrical charges is maximum until decrease to the certain value, which is q. Okay, so this one, if I integrate, will be t over cr, and this is the t0. So what I have here is actually q minus ln q naught. So this is the t over cr. So if I about to combine this ln, so the subtraction is actually equals to the division of the for the ln, sorry, I repeat again. So for the ln, the subtraction is actually equals to division. So ln q over q naught is actually equals to the t over cr. So this q over q naught, so if I'm about to move this ln to the other side, so what I have here is actually exponential t over cr. So this q, finally, what I get for this q is actually q naught e to the power of t over cr. So this is the final equation for the electrical charges for the discharging CR circuits. Okay, so this is the first one. So we have done for the first one, which is the electrical charges. So let's move on to the second one, which is the potential difference across the capacitor. Oh, I missed something, which is the graph for the Q against T. So basically, what I get is actually equals to this type of graph. So basically, the electrical charges is actually decreasing along with time t. Okay, so this is the graph. Okay, so let's move on to the potential difference. So what will happen to the potential difference? So this is q e minus t over cr. So we know that q is actually equals to cv. So this q naught, the potential difference will be maximum, which is cv naught e to the power of t over cr. Okay, so if I about to cancel this each other, so what I have here is actually v is actually equals to the v naught multiplied by e to the power of negative t over CR. So what I have here for the potential difference along with time t, so this will be the curve. So this one is actually the V0 initially. Okay, so yeah, this is the final equation and the final conclusion of the graph for the discharging CR circuits. So basically the potential difference is actually decreasing as the electrical charges decreasing when the capacitor is discharging. Alright, so let's move on to the electric current. So basically we talked from the previous parts, we said that the electric current is actually decreasing when the capacitor is about to discharge, since the electrical charges will also decrease. So hence, what will be the formula? So basically from the Q is equal to the Q naught e to the power of negative t CR. So we know that I is equals to the dq over dt. So what I have here, dq over dt. So if I about to differentiate this one, so what I have here is actually negative t over CR. So the exponential remain constant. Alright, so to be reminded that for the discharging circuits, so the electric current is actually negative dq over dt, since the I is keep decreasing. So I about to add this both sides by negative. So this is the negative dq over dt. So negative is actually equals to positive. Sorry, this one should be 1 instead of t. So this one is actually 1. So negative positive. So q over CR multiplied by the exponential to the power of negative t over CR. So negative dq over dt basically is equals to I. So q over c, what I have here is actually V0 over R. So this is the same. So what I have here is actually I0 e negative t over CR. This is the final equation for the electric current. Okay, so as for the graph, so what will be the graph here? So the graph basically is the same as the electrical charges and the electric potential difference, which is the exponential curve. So this is the I0 and this is the curve. So basically, I repeat again, so basically the electric current inside the circuit is decreasing due to the electrical charges inside the capacitor when the capacitor is discharging will also decrease. Okay, so this is the concept for the discharging circuits. So let's move on to the next part. So we are still inside the discharging circuits. Okay, so let me just observe what will be the next. Alright, so we have already discussed the electrical charges, the electrical potential difference across the capacitor and the electric current. So let's just discuss about the graph. So the graph of ln Q against T. So sometimes the how should I inscribe this one? So sometimes the question will also ask about the graph for the discharging circuits, but in this case the graph is actually represented in a straight line. So this one is T. So basically we learned just now, what we learned just now is actually Q. So in this case, for the straight line, so this Q is actually the ln Q. So this is the ln Q naught, if I'm not mistaken. So let's just see one by one. So from the basics, Q is actually equals to the Q naught E negative T C over CR. So if I about to add both sides by ln, so what I have here is actually ln Q. So this is the ln Q naught E negative C over, sorry, to the power of negative T over CR. So the multiplication for the ln is actually the addition between the two variables. So what I have here is actually the ln Q plus the ln E negative T over CR. So the ln E, ln and the exponential will be cancel out each other. So what I have here is actually equals to negative T over CR. Okay, so if I rearrange the equation, so what I have here is actually negative T over CR plus ln Q naught. So the ln Q naught is actually the y-intercept for the straight line. So this T is actually the for the x-axis, and the ln Q is actually for the y-axis. So this is how the straight line form in terms of ln Q and T. Alright, so we have done for this graph. Okay, so there's another graph. Okay, so let me just erase this one. Okay, so in this case, for the next graph, we're going to see what will happen for the graph of ln V against T. Okay, so we know that from the previous parts, we talked about the Q is actually equals to the Q naught E negative T over CR. So Q is actually equals to CV. So CV naught E negative T over CR. So this can be cancelled. V is actually equals to the V naught E negative T over CR. So this is just actually the beginning. So if we're about to add both sides by ln, so this is ln V and this is ln V naught multiplied by exponential to the power of negative T over CR. So this is basically same as the concept of electrical charges. So the ln, the multiplication is actually equals to the addition. So this is ln V naught plus the ln E negative T over CR. So the ln and E will give us 1. So okay, let me just observe for a while. So this power will be moved to this side. So what I have here, the ln E, the ln and the E will basically give us 1. So finally, what I get is actually negative T over CR. So basically the final equation is this form. So this will give us the straight line as well. So this is the T and this is the ln V naught. So this is the this basically is the concept of the ln V against T. Alright, so we've done for the both graph, which is the ln Q and the ln V, which against time T. Alright, so let's move on to the final part for our chapter of the capacitor, which is the time constant for the discharging circuits. So basically just now we discussed about the time constant for the charge for the chargings of the CR circuits. So for this topic, we're going to talk about the time constant for the discharging circuits. So basically we know that the time constant, which is the T light symbol, is actually equals to the CR. Okay, so from this formula, Q is equals to the Q naught multiplied by E to the power of negative T over CR. So for the first time constant, which is the Q negative CR over CR, so what I have here is actually equals to the Q over E. So what will be the value? So the value is actually 0.37 of Q naught. So this is the first time constant. As for the second time constant, okay, so Q is actually equals to Q naught E negative 2CR. So I discussed just now, the second time constant is actually equals to the 2CR. So this one is the CR. So what I get for the final equation is actually equals to the Q naught over E squared. So basically this is the 0.135. So from the value, we can see that the electrical charges, the value for the electrical charges is actually decreasing. So this shows that the electrical charges inside the capacitor is actually decreasing. So it means that, sorry, I repeat again. So the electrical charges basically is decreasing. So for in the condition when the capacitor is discharging with the resistor, of course. So this is basically the concept for the time constant. So as the time constant getting longer, and hence the value for the electrical charges will decrease. Alright, so I think that's all for the capacitor, the chapter of the capacitor. So we have done for all the chapter, all the subtopic for this chapter. So I think we'll stop here now. So if there's any question need to be asked, please comment below this video. So I'll see you next time. Thank you. Bye.